Hello students, in this video we will discuss about concepts of process management. So before we go into the actual topic, we shall first see what is a process. A process is the instance of a computer program that is being executed by one or many threads. And this process contains the program code and its activity. Depending on the operating system, a process may be made up of multiple threads of execution that execute instructions concurrently. So, a process can execute instructions concurrently. While a computer program is a passive collection of instructions, a process is the actual execution of those instructions. So the computer program is being executed. The actual execution is done by this process. Coming to the process in Unix. The active entities in the Unix system are called as processes. And these processors are similar to the classical sequential processes, and each process run on a single program and initially has a single thread of control. In other words, it has one program counter which keeps track of next instruction to be executed. Most Unix versions allow process to create additional threads once it starts executing. Unix is a multi-programming system, so multiple independent processes may be running at the same time. Each user may have several active processes at once. So on a large system, there may be hundreds or even thousands of processes running. In fact, on most single user workstations, even when the user is absent, dozens of background processes called daemons are running. These are started automatically when the system is booted. A typical daemon is the cron daemon. It wakes up once a minute to check if there is any work for it to do. If so, it does the work. Then it goes back to sleep until it is time for the next check. This daemon is needed because it is possible in Unix to schedule activities in minutes, hours, days, or even months in the future. For example, if a user has a dentist appointment at 3 o'clock next Tuesday, you can make entry in the cron's daemon database telling the daemon to beep him at say 2:30. When the appointed day and time arrives, the cron daemon sees that it has work to do and starts a beeping program as a new process. The cron daemon is also used to start up periodic activities such as making daily disk backups at 4 a.m. or reminding forgetful users every year. Other daemons handle incoming and outgoing electronic mail, manage line printer queue, check if there are enough free pages in the memory, and so forth. Daemons are straightforward to implement in Unix because each one is a separate process independent of all other processes. Coming to fork in process. Processes are created in Unix in an especially simple manner. The fork system calls creates an exact copy of the original process. The forking process is called the parent process. The new process is called as child process. The parent and child have their own private memory images. If the parent subsequently changes any of its variable, the changes are not visible to the child and vice versa. That is, if the changes are made in the child, it is not seen by the parent. Open files are shared between parent and child. That is, if a certain file was open in the parent before the fork, it will continue to be open in both the parent and the child afterward. Changes to the file by either one will be visible to other. This behavior is only reasonable because these changes are also visible to any unrelated opens the file as well. The fact the memory images, variables, registers, and everything else are identical in the parent and child leads to a small difficulty. What is that difficulty? How the process know which should run the parent code and which should run the child code. For this, the secret for this is the fork system calls return a 0 to the child and a non-zero value, the child's PID to the parent. Both processes normally check the return value and act accordingly. These processes are named by their PID. PID stands for process identifier. When a process is created, the parent is given the child's PID. If the child wants to know its own PID, there is a system called Get PID that provides it. PIDs are used in a variety of ways. For example, when a child terminates, the parent is given the PID of the child that just finished. This can be important because a parent may have many children. Since children may also have children, an original process can build up entire tree of children, grandchildren, and further descendants. Process in Unix can communicate with each other using a form of message passing. It is possible to create a channel between two processes into which one process can write a stream of bytes for the other to read. So here we can create one process which can write a stream of bytes for the other to read. These channels are called as pipes. Synchronization is possible because when a process tries to read from an empty pipe, it is blocked until data are available. Shell pipelines are implemented with pipes. When the shell sees a line like sort, this is the format or the syntax, it creates two processes, sort and head, and sets up a pipe between them in such a way that the sort's output is connected to head's input. In this way, all the data that sort writes go directly to the head instead of going into a file. If the file fills up, the process stops running sort until head has removed some data from the file. The process can also communicate in another way. Software interrupts. A process can send what is a what is called a signal to another process. Processes can tell the system what they want to happen when a system arrives. The choices are to ignore it. You can ignore it, to catch it, or to let the signal kill the process. If a process elects to catch a signal sent to it, it must specify a signal handling procedure. It should also specify the signal handling procedure. When a signal arrives, control will abruptly switch to the handler. When the handler is finished and returns, control goes back to where it came from, analogous to hardware I/O interrupt. This is very much similar to our hardware I/O interrupts. The process can only send signals to members of its process group, which consists of its parent, siblings, and children. The process may also send a signal to all the members of its process group within a single system call. Signals are also used for other purposes. For example, if a process is doing floating point arithmetic and it invariantly divides by 0, it gets a SIGFPE, floating point exception signal. Many Unix systems have additional signals as well, but programs using them may not be portable to other versions of Unix. One programs of Unix may not be working with the other version of Unix. Now we'll see what is the process management calls in system calls in Unix. Let us look at the Unix system calls dealing with the process management. Fork is the only way to create a new process in Unix system, and it creates an exact duplicate of the original process, including all the file descriptions, registers, and everything else. After the fork, the original process and the copy go their separate ways. All the variables have identical values at the time of fork, but since the entire parent code image is copied to create the child, subsequent changes in one of them do not affect the other one. Once it is copied and they are sent separately, if there are any changes being made, they will not affect each other. Fork call returns a value which is 0 in the child. If it is a child process, then it returns a 0 value and equals to child's PID in the using the return PID processor identifier. The two process can see which is the parent and which is the. In most cases, after a fork, the child will need to execute different code from the parent. So consider the case of the shell. It reads a command from the terminal, forks of a child process, waits for the child to execute the command, and then reads the next command while the child terminates. To wait for a child to finish, the parent executes a wait PID system call which just waits until the child terminates. Wait PID has three parameters. The first one allows the caller to wait for a specific child. If it is one, any old child will do. The second parameter is the address of the variable that will be set to child's exit status. The third one, whether the caller blocks or returns if no child is already terminated. In the case of the child process must execute the command typed by the user. It does this by using the executing system call, which causes its entire core image to be replaced by file named in its first parameter. Here there are three ways or three parameters. It should wait to call the specific child. The second parameter is the address of the variable that should be set to the child's exit status, and third one whether the caller blocks or returns if no child is already terminated. So these are three parameters which we have to consider. Next is implementation of process in Unix. So it is not very easy as and this is similar to an iceberg. What you see is part above the water, but there is also an important part underneath. So not just the thing what we see, there is an other things which are to be considered. Every process has a user part that runs the user program. However, when one of its threads makes a system call, it traps to kernel mode and begins running in kernel context with a different memory map and full access to all machine resources. It is still the same thread, but now with more power and also its own kernel mode stack, kernel mode program counter. These are important because a call can block part way through, for example, waiting for a disk operation to complete. The program counter and registers are then saved so the thread can be restarted in kernel mode later. The kernel maintains two key data structures related to process, the process table and the user structure. The process table is resident all the time and contains information needed for all the processes even though that are not currently present in the memory. The user structure is swapped or paged out when it is associated process is not in memory in order not to waste memory on information that is not needed. The information the process table falls into the following broad categories. So the information which is present in the table, it falls under the following categories. The first one is the scheduling parameters. So in this scheduling parameters, it contains what is the process priority, the amount of CPU time consumed recently, amount of time spent sleeping recently. Together, these are used to determine which process to run next. Memory image, pointers to the text, data and stack segments, or if the paging is used to the page tables. If the text segment is shared, the text pointer points to the shared text table. When the process is not in memory, information about how to find its part on disk is here too. Next come the signals, mass showing which signals are being ignored, which are being caught, which are being temporarily blocked, and which are in the process of being delivered. Next comes the miscellaneous, current process state, even being waited for, if any, time until alarm goes off, PID of the parent process, and user and group identification. The user structure information that is not needed when the process is not physically in memory and runnable. For example, Although it is possible for a process to be sent a signal while it is mapped out, it is not possible for it to read a file. For this reason, information about signals must be in the process table. So they are in memory all the time, even when the process is not present in the memory. On the other hand, the information about the file descriptors can be kept in the user structure and bought it only when the process is in memory and runnable. The information contained in the user structure will have machine registers, which will have when it wrapped to the kernel occurs. The machine registers, including floating points, are saved here. System call state. It contains the information about the current system call, including the parameters and as well as results. File descriptor table. When a system call involving a file descriptor is invoked, the file descriptor is used as an index into this table to locate the encode data structure, which is called as inode, corresponding to this particular file. Accounting pointer to a table that keeps track of user and CPU time used by the process. Some systems also maintain limits here on the amount of time CPU time a process may use, maximize of its stacks, number of page frames it may consume, and other items. Kernel stack, a fixed stack for use by the kernel part of the process. Bearing the use of these tables is mind, now it is easy to explain how processes are being created in Unix. So we'll see how the process are created in Unix. When a fork system call is executed, the calling process taps into kernel mode and looks for a free slot in the process table for use by the child. If it finds one, it copies all the information from the parent's process table entry to the child entry. It then allocates memory for the child's data and stack segments and make exact copies of the parent's data and stack segments there. The user structure is copied along with the stack. This text segment may either be copied or shared since it is only read. At this point, the child is ready to run. When a user types a command is on the terminal, the shell creates a new process by forking off a clone of itself. The new shell then calls executive to overlay its memory with the contents of the executable file. So this is how a process is being created in Unix. Thanks, and we'll continue the next topic in the next video. Thank you.